Last video, we defined the expected value, one number that summarizes a whole PMF. This video, that idea grows into a toolkit. We'll learn to average any function of a random variable directly from its PMF, no derived distribution needed. Check the recipe on a radio contest, and then meet the two summaries that dominate all of probability: the mean, which is a center of mass, and the variance, which measures spread. We finish with the algebra that ties them together, what happens to both under shifting and scaling. Suppose y equals g of x and we want its mean. We know one route already. Build the PMF of y from pre-images, like last chapter, then apply the definition. That works, but there is a shortcut. The expectation of g of x can be computed straight from the PMF of x, sum g of x times p sub x of x over the range of x. Evaluate g on each value, weight by the original masses, add. Two quick checks. If g is the identity, this is just the mean from last video. The definition subsumes it. And if g is a constant c, the masses sum to 1 and the expectation is c itself. One more. With real content, let g be the indicator of a set S, 1 inside S, 0 outside. Then the expectation of the indicator of x in S is exactly the probability that x lands in S. Probabilities are expectations. Keep that. It pays off across the course. Let's test both routes on the same problem. A radio station runs a contest. 100 cards in a drum, 3 drawn. Each winner gets $1,000, but each person can win only once. David mailed in 50 of those 100 cards. Let X be how many of the 3 drawn cards are his. Its PMF comes from counting. Choose K of his 50 and 3 minus K of the other 50. His winnings are g of x, 1,000 times the minimum of x, and 1. Route 1, the direct formula, sum g of k times the mass of k over k equals 0 to 3. The 0 term drops out, the rest collapse, 1,000 times 29 over 33. Route 2, through y itself. Y is either 0 or 1,000. The chance of 0 is the chance none of the 3 cards is David's, 4 over 33. So y equals 1,000 with probability 29 over 33. Same product. Both routes, one answer, about $879. That agreement is a theorem, not luck. Group the values of x by where g sends them, and the two sums rearrange into each other. The simplest expectation deserves a picture. Take the PMF of x and build it physically. At each value x, place a particle whose mass is p sub x of x. Here is a Bernoulli with mass 1/4 at 0 and 3/4 at 1. Ask a mechanics question: where does this system balance? The center of mass is the mass-weighted average of the positions, and that is, symbol for symbol, the formula for the mean. This system balances at 3/4, the mean of the Bernoulli. The mean is where the PMF balances. The named distributions each come with a mean worth remembering. A geometric with parameter p balances at 1 over p, and a binomial with n trials balances at n times p. Results will lean on constantly. The mean says where a distribution sits. It says nothing about how widely it spreads. These two PMFs balance at exactly the same point, but one hugs its mean and the other scatters. We need a second number. Measure each value's deviation from the mean. Square it so that left and right count alike, and take the expectation. That is the variance, the expected squared deviation from the mean. It is never negative, and it is large exactly when mass sits far from the balance point. Its square root is the standard deviation, sigma, the spread in the same units as x itself. For a Bernoulli with parameter p, the variance works out to p times 1 minus p, largest at 1/2, where the outcome is most uncertain, and the Poisson is famous for this. Its variance equals its mean. Both are lambda. Finally, the algebra. Take y equals ax plus b, an affine function, scale by a, shift by b. What happens to the mean and the variance? Shift first. Slide the whole PMF right by b, and the balance point slides with it. The mean of x plus b picks up exactly b. The spread doesn't change at all. Shifting moves a distribution, it does not widen it. Now scale by a. The balance point scales to a times the mean. But deviations from the mean scale by a too, and the variance squares them. So the variance picks up a squared. The mean of ax plus b is a times the mean plus b. The variance of ax plus b is a squared times the variance. The shift b is gone entirely. Behind the first rule is something more general. Expectation is linear. The expectation of a sum of functions of x is the sum of their expectations. Constant slide out, no independence, no fine print. The key idea of this video: average a function through the PMF directly, and its two star cases, the mean and the variance.